All right, so I want you all to welcome our first speaker, Oana Balmau. She's an assistant professor of computer science here at McGill University and leader of the DISCS Lab, which stands for Data Intensive Storage and Computer Systems. Her research focuses on storage and data management systems with an emphasis on large-scale data management for machine learning, data science, and edge computing workloads. Before McGill, she completed her PhD in computer science at the University of Sydney, having previously studied at EPFL in Switzerland. Oana has also held a number of positions in industry, working with Nutanix in Silicon Valley and in the Bangalore office, with ABB Research in Switzerland, HP Vertica in Cambridge, Massachusetts, and Nethermind in London. She's also a part of MLCommons, an open engineering consortium aiming to accelerate machine learning innovation and increase its positive impact on society through designing public data sets, benchmarks, and best practices. So without further ado, welcome, Oana. I welcome you to share your screen now.
Thank you, Loic. Let's see if my presentation will live up to your very nice introduction.
I have no doubt.
Can you all see my screen? Is everything okay?
Yeah.
Yeah. All right. Well, thank you all for coming. It's nice to see all of your faces here. I'm honored to be the first one in this talk series. So today I'm going to try to give an overview on a high level of some of the challenges that exist in modern storage stacks. And in the title, I say that they're deep and heterogeneous. So as I was thinking about how to best introduce this, I thought that the best way for you to get an idea of what it means to do storage research is to show you a concrete example that I was working through in my PhD. So if you like that kind of work, maybe that would be some inspiration for you to further continue this exploration in storage. Since this is a pretty short slot, I'll encourage everyone to maybe put the questions in the chat and we can go over them in the Q&A. So I get the chance to cover everything in these 20 minutes. Does that sound good? All right.
Yeah.
So as Loic was saying, I have created DISCS Lab a year ago. And our main focus is to look at data-intensive workloads and accelerate these workloads, better support them from the point of view of storage. And some of the main challenges that we're dealing with are growing data sets, which are getting into the petabyte scale. We are also dealing with the fact that we want insights on this incoming data to be fresh. And finally, we're dealing with this mixed nature of the workloads. And I'll tell you more about what this means in a minute. Now, our approach in the lab is kind of based into three different pillars. So first, we need to know what the new storage hardware gives us to be able to better support these workloads. Then, after studying the properties of the new hardware, we're trying to redesign key components of existing storage systems. And examples of these key components can be caches, indexes, better layouts on disk, better concurrency, and so forth. And if it's absolutely necessary, we're not afraid to build systems from scratch either. So today, I'm going to lead you a little bit into kind of the first and the second step, where we understand the characteristics of storage, and then we're going to do a little bit of detective work to figure out what's wrong with existing storage systems. But before telling you about that, I'd like to set the context a little bit more. So, as I was saying, our first challenge in data management is that we're producing, and we will keep producing, huge amounts of data. So the growth of our data production is estimated to be exponential. And what this means from the storage perspective is that the data won't be able to be stored completely in memory as we're doing analytics or using it to get insights. So more and more, we'll have to serve it efficiently directly from disk. And by efficiently here, I mean that we need high throughput. This means how many operations can you do per second. We need low latency, which means how fast can you serve a request. And also, last but not least, we need to be efficient with the way that we use space. Because even though the devices are getting larger and cheaper, the data is growing faster than the storage devices can keep up. And just for the record, 1 zettabyte is 1 billion terabytes, just to give an idea of scale. Now, in addition to the fact that we're producing a lot of data, the nature of this data is also very diverse, and we're using it differently from the past few years. And let me illustrate this with an example. So in the past, and still now, a lot of the way we were interacting with the data is through different flavors of recommendation systems. So this is an example of book recommendations in Amazon, where we are using vast databases to distill some insight in this recommendation. Now, the workload is heterogeneous in the sense that we have reads and writes. So for the writes, we have these new impressions coming, and they need to be collected in a write optimized database. And on the read side, we need to first read the data and scan it to be able to perform analytics and learn from it. But also we need to read the actual insights when we're performing inference. However, you can see that these two parts of ingesting incoming data, performing analytics, and then the data serving part are relatively separate. So typically what happens in industry is that there are two parallel pipelines that are dealing with the same data set. So one pipeline is about data ingestion, and the other one is about analytics. And as a consequence, because these two pipelines aren't perfectly synchronized, we get to have insights on relatively old data, which could be days or even weeks old, depending on how big the model is and how often the retraining is done by in that particular recommender system. And in this example with the book recommendations, maybe you don't change your preference every few weeks, but there are cases where we need to be able to react much faster. And by much faster, I mean in real time. So you can think of going from a recommendation in a matter on data that's a few days old to a recommendation based on data that's a few seconds old. This is the scale difference. And the example that I like to give here is an Internet of Things workload or edge computing. So here again, we have this mixed workload of transactional and analytics. And by the transactional part is where the writes done by the sensors are being continuously recorded. On the read side, we again have the analytics piece. But the catch here is that we want the analytics to be done on fresh data, to be able to give some recommendation for these sensors or the devices that are controlled by these sensors to be able to adapt to real-time conditions. So as you can see, this problem is a lot tougher, and it will require all of our knowledge of hardware and systems level optimization. Going back to our data growth graph, one more thing that I would like to add is that the nature of the data in these new types of IoT workloads is also quite unstructured. So by unstructured I mean that the data has a wide variety of types and sizes, ranging from, for example, a few bytes to store an integer to a few hundreds of megabytes to store a video. And in addition to that, also the relationships within the data keep changing as the applications and the sensors evolve. So how can we handle all of this unstructured data? And this is where our research comes in. So part of the research that we're doing in the lab is focused on these very fast kind of NoSQL databases called key value stores. You can think of key value stores as a hash table. So they're very simple, very fast data structures that contain a key value pair. So a key is, you can think of it as the hash key in an index, and then the value is whatever we want to store in the data store. So these key value pairs can have multiple sizes and multiple data types. However, the price that we pay for this kind of flexibility is in the kinds of operations that we can do on the data. So key value stores have a very simple API, which consists of put, which means write, get, which means read, and scan, which means traversing a range of items in a lexicographic order or whatever ordering the elements have. Now, this may seem like a very simple example, but key value stores are a crucial component in many industry scale systems. And here, just to name a few, maybe you've heard of some of these. Cassandra is following that's this kind of structure, Roxy, MongoDB, Amazon's DynamoDB, etc. So to give a concrete example of how large these key value stores can get, Apple runs a Cassandra cluster of, last time I checked, around 80,000 nodes backing iCloud. So they can get quite big, and they're very good for scalability. So on the software side, we have these key value stores that are offering us some flexibility and some speed. But what's happening on the hardware side in storage? So the reality is that the storage hardware landscape is very exciting these days, and it's changing very fast. So this picture might be familiar to some of you, and this is what storage used to look like until around 10 years ago. So we had the story was quite simple. We had main memory, which is small, fast, and volatile. By volatile, I mean that once the machine is turned off, the data is lost. Then we had these hard disks that were cheaper, slower, and larger, and persistent. And then maybe we had tape for archival purposes, not really in personal computers, but large companies use tape for archival still. However, things have changed a lot over the past 10 years. And this is where the deep heterogeneous storage hierarchy comes into play. In addition to main memory, hard disk, and tape, we have a whole range of devices of each of the ends of the spectrum. So if we look at the archival storage media, and I'm not going to insist on this too much in this talk, but we have research developments to archive data in glass at Microsoft, or even in DNA. And then at the other end of the spectrum of more faster storage devices, we have SSDs and non-volatile memories, which were only out a few years ago commercially. So today, as you can imagine, in the remaining 10 minutes, we can't cover all of the storage hierarchy. So I decided to focus more on SSDs to give you an idea of the kinds of things that can happen when these storage devices are changing. So probably you've heard of SSDs and you have SSDs already in your machines, but many new things have happened in this landscape. So what's new with SSDs? First of all, the server-grade SSDs now are much faster. So this plot shows a sketch of the evolution of bandwidth in SSDs over the past 10 years. And as you can see, the write bandwidth has been growing by an order of magnitude compared to 2010. In addition to that, we also have the very interesting property that random access is almost as good as sequential access. which was not the case 10 years ago. So if you look at this plot, where in blue we have the sequential writes, and in red we have 4K random writes, you can see that you can't really see it in 2010, but it's more visible in 2013 that there is a gap between sequential and random access. However, this gap is completely closed with new NVMe SSDs. So we have all these changes in hardware. Really, the question that a lazier programmer would ask is, do I need to change anything? I mean, don't things that are already there work? I mean, maybe these new SSDs would just make existing systems go faster. So that was exactly what we tried to do when we first got our hands on one of these SSDs in the lab. This was back in the PhD days. So we bought one of these new NVMe SSDs for the lab, and we wanted to try it out, right? So our prediction of performance of one of these existing key value stores that I was mentioning earlier, here I'm going to pick on RocksDB, which is a key value store that was developed at Facebook, but now it's open source and it's used to back so many types of workloads that are write intensive. So for example, in addition to social media and indexing, RocksDB is also used for blockchain applications. So going back to this plot, we were looking at the speed of the device and the workload that we were going to use, and back of the envelope simple performance computation predicted that the performance of RocksDB should be around this blue line. However, when we actually ran the workload, there was a big surprise. So RocksDB had very low and unstable throughput. Now, to be able to understand this result of overall end-to-end throughput, we needed to dig a bit deeper. And the first thing that we looked at was the I/O bandwidth utilization. And I/O bandwidth means how fast can the database access the SSD, right? And as I will explain in the next few minutes, these types of key value stores are very I/O bandwidth hungry. So the expectation was to see that RocksDB is maximizing this I/O capacity. However, again, as a surprise, we saw that RocksDB wouldn't even use half of the available bandwidth, even though it's notorious to be a bandwidth hungry system. Continuing this investigation even further, and this is it's typical in systems work, we looked at the CPU utilization in RocksDB. And this is really the key of the mystery. So as you can see here, this plot shows the CPU utilization over time. And for the entire duration of the experiment, we can see that RocksDB was running at maximum CPU utilization. And what this means is that fundamentally, the design of RocksDB isn't suitable for this new type of hardware because the system isn't capable to saturate the I/O bandwidth because it becomes CPU bound first. So, like more in plain English, what this means is that all that extra performance that you would get by buying a new and fancy storage device would be lost because the system needs more cycles, more CPU cycles to saturate the device. So I'd like to spend the next few minutes giving you an insight of why this happens. I mean, we've seen all these measurements, but what really happens inside RocksDB that makes it CPU bound? And to be able to understand this, I need to give you a little overview of the architecture of this database, but we'll keep it high level. So RocksDB's design is a log structure merge key value store. And this is a class of key value stores that is very popular right now for write heavy workloads. And the log structure merge key value stores are at a high level split into two components. We have a memory component and a disk component. The memory component is used to absorb write workloads, because remember, the assumption is that the disk is slower than the memory. So we will absorb all of the incoming writes into this sorted write buffer. And when the buffer is full, we're going to write it in one go to the disk. And this is how we obtain these sorted immutable files on disk. By immutable here, I mean that once the file is written on disk, we don't change it. So we will need to do some other trick to modify files. So let's quickly go through an example. Say we want to write some things to this database. So the clients keep writing. Eventually, this sorted buffer will get full. And when it gets full, it's going to be temporarily replaced by a new empty buffer, and the old one is going to be written to disk. So this is done in one operation, which is very good for all devices because it's one large sequential write. Now this happens again and again, and if we keep doing what I just said, we will end up with many files on disk, right? And possibly some duplicate files, because remember, we can't modify a file once we've written it to disk. So if we want to modify the same key, we will have to put it into another file. So then we could end up with two keys, an old version and the new version existing in two separate files. So we need a way to merge these files to be able to do some cleanup, right? This merging is well, it's a more complicated operation in a log structure merge key value stores, but on a high level, according to some policy, some files are chosen from disk, they're loaded into main memory, and they're being merged. So the merging, you can think of it as a merge sort. So the two files are traversed, and if the same key is found in both, the new version of the key is taken and it's written into a new file. And this operation is relatively CPU intensive because in addition to traversing these files, we also need to create some helper data structures like indexes all over again. Right. So once the two files have been merged, the new file is written to disk and all is good. This is now you're experts in log structure merge key value stores. And I hope that you can appreciate this plot a bit more, the plot that we just saw. So indeed, if we look in more detail at why RocksDB is using 100% of the CPU, we will see that it's spending 60% of its time merging and creating indexes of these new data structures. So really, the main assumptions that these old key value stores were making about the hardware no longer hold. They were assuming that I/O was the bottleneck, so they could use CPU cycles to do whatever they wanted just to optimize for the I/O, which is no longer the case, as we have seen. And they would also assume that the long sequential writes are much more efficient than short random writes, which again, if you remember, we have seen that it's not the case. Now, because of these assumptions, key value stores are doing a bunch of, say, poor design decisions for new hardware, such as making efforts to ensure large and sequential writes, which lead to using shared data structures that lead to contention, and also these expensive maintenance operations that we just saw. So this is the end of our exploration, which leaves us the question, how we should redesign key value stores for fast drives? Well, I'm not going to tell you today. If you want to know more, you can check out our website. You can write me an email and have a chat. However, there are many open challenges in the storage space. Many different. Today I showed you what can happen with SSDs, but there are also even more challenges that come when adding persistent memory to the mix. and even more interesting questions when we're starting to look at how to combine all of these layers together. So I'd like to end this talk by thanking you all and thanking my students, without whom all of this work wouldn't be possible. So now I'll open it up to you for questions.
Woo, that was a great talk. Thanks a lot. You know, it's cool because on the computer science side, you know, maybe less than like electrical engineers, we don't necessarily have this vision of the hardware. And so many exciting things are happening that we don't see necessarily. And I also really love the fact that you can see kind of the more empirical measurement stuff that happens on the system side where you investigate. So that was really cool.
I'm glad you enjoyed. Yeah, I think the most interesting things happen when we combine the hardware and the software.
Yeah, for sure. All right, so everybody can ask a question if they want to. I think we can stay on for like another 10 minutes just to like network and hang out.
I can stick around for another 10 minutes. Also, you know, if you watch this presentation again and your questions are coming, don't hesitate to write. I always love to hear from students. Somebody's
asking if you'll post the slides.
I could, sure. I can send you the slides.
Cool. Yeah, if you send them to me, we'll distribute them. Something I'm wondering about that you mentioned is that, you know, you have the KV stores, which have the very simple API. So you get large objects by key. So then that means if you're trying to do some kind of complex data processing, that will then happen somewhere else, you know, not in the database itself. And so when you have very complex workloads or whatever, something that you could do in like a SQL database, like a join or anything, that takes this responsibility to another kind of system that is kind of like a question mark in my mind right now. So like these kind of systems will also have to be extremely fast and efficient, especially in like real-time workloads. So I don't know if you have some insight about how they handle that.
Well, this is kind of an open question, honestly, in database research, because it's exactly like you say, like you have on this side very simple kind of key value pair hash table structures, and then you have these kind of databases that were optimized to do everything. You know, they're very rich, and you can handle queries that are much more complex that you can do with key value stores. Now there's a trend overall to meet somewhere in the middle. So there's more research going to kind of adding new types of operations to key value stores to support more complex analytics, but without getting into the bloat that traditional relational databases have to keep them lean. What I've seen done in industry so far is that these key value stores are scanned by, you can think of it as a MapReduce job. So it's those jobs that are taking care of the degree of parallelism, and then, you know, doing the mapper work and then reassembling the results. So I guess that's the question mark system that you were talking about.
Okay, that's very interesting. So there's a question in the chat. Here.
Yeah, so from Mathieu. All right, it's preceded by saying you don't know too much about databases. Would increasing the memory help to make CPU processing relatively faster? Can I just buy more RAM to optimize the database? Right, so you can always throw more money at the problem. The issue is eventually it won't make sense to buy more hardware, because as you saw, the data keeps growing. So if you can afford to keep up by just buying more memory, and eventually that would mean buying more servers, because even in one server, the memory slots are limited. So you would have to scale out. Then you would have this added layer of handling a distributed system. So it's unclear whether what you gain by storing data in memory, you lose by having to handle multiple machines and handling failures and the synchronization and so forth. So it's not an easy answer. see one more question from Aristide. Are traditional relational databases also running up against the same CPU-bound issues in light of new faster storage mediums like the key-value stores due to being founded on similar assumptions like you mentioned? I think I would say the relational databases have slightly different problems. I mean, for sure, they would run into a similar issue, but before that, I think they would run more into synchronization issues, like locking and join execution, because a join is a fairly complex operation where you need to synchronize, and it's hard to parallelize. The beauty of these key value stores is that the operations are so simple that you can just assign a chunk of the data to a specific thread, and then you don't need to worry about synchronizing concurrent accesses and so forth.
I have a question.
Mm-hmm.
So that the fact that the CPU gets well, the CPU is a bottleneck when you have like we're wasting performance because we're in the environment of a single computer, right? Yeah, CPU gets to 100% while we still do not feel the possible throughput, right? I was wondering if it's also like a legitimate solution to try to disaggregate the resources, as we have if we're in a data center environment, right? And have machines which are just full compute, but have a storage cluster.
Yeah.
Okay.
Yeah, absolutely. That's definitely something that a lot of research is looking at right now in data centers, and disaggregation is, I think, is a good answer to what's happening. Then the question is, how do you size? What's the right ratio between different types of storage and different types of compute?
Can you expand a bit on what disaggregation is and how it would solve the problem?
Sure. So basically, disaggregation means that instead of having one computer that has this amount of CPU and this amount of storage, and you try to kind of optimize your software with the hardware that you have available, rather than doing that, and disaggregation is usually done in data centers, so you wouldn't do it for one machine, but you would look at the resources of the data center in terms of compute resources. So this could be CPUs, GPUs, TPUs, and so forth. Then you can look at, and then you can have the storage resources that are disaggregated. So when I say resources, I mean a compute resource would be a server that doesn't really have a lot of storage, but has very powerful processors. And by storage resources, I mean the opposite. So a server that doesn't really have that much CPU, but has, say, a big amount of fast SSDs, 10 parallel fast SSDs. So the question becomes now how to transfer efficiently the data from these storage resources into the compute resources. And the beauty is that you could pair them depending on the workload. You could give more of these servers, say, compute intensive and less storage, or you can mix and match in any way you like. So that's why Sebastian's point was very good. That's one way to scale different workloads. Like in this example, if you imagine that magically you could give more CPU to the workload, you would solve the issue, right? Because there would be enough compute cycles to be able to handle the new SSD.
Yeah, that's crazy. And then you get a bunch of management overhead, I guess. And some meta structure to handle dispatching, all that.
Yeah, the thing is, in a data center anyway, you would have to have that. So you could just kind of build onto the scheduler that exists already. Okay. The question is more, I think, how do you choose how much to give to each workload, which I think is an open question in research. Yeah, these are all great questions, guys. I'm glad it maybe this is a sign that you followed the talk. I will have to drop off, unfortunately, but it was a pleasure to hang out. And please don't hesitate to reach out if you ever have questions.
Cool. Well, thanks a lot for your time and for this great presentation.
Thank you for inviting me, Luke.
Yeah, no worries. My pleasure.
Thank you so much for the talk. It was great.
Thank you.
There's some additional questions in the chat. I can send them to you by email after.
Yes, please. Yeah.
Cool.
Bye now.
All right. Have a good one.
Bye. Thanks.
Bye.